The title of my talk is how we can utilize natural polymers, particularly cellulose and biochar based composites for water purification. I will show you a couple of slides from India where I really belong to which laboratory. My university was the first in the country named after the father of the nation, Mahatma Gandhi. And you see where I'm located, very, very south of India. This is called Kerala. And Frank and Mawa was with us 2 times. This is our campus, university. You can see when I was the vice chancellor of the university, we received the best university award 3 times from the chancellor of the government of Kerala, 3 times. This is our campus, very green campus. We have a large number of international cooperation with the different universities across the globe. This is our new, complex for the Nano Center, energy. All the schools are placed in the new building. This is called Academia Complex. So coming to our presentation today, let me show you a very brief outline about the water scarcity. We all know the famous quote, water, water everywhere, but nary a drop to drink. Dear colleagues, 70% of the Earth's surface is covered with water. But if you look at the reality, what we have is less than 1% of world's fresh water is available to mankind. So very small quantity of water. And if you look at the recent United Nations report, in 2025, 1.8 billion people worldwide will have live in absolute water scarcity. So that's very important point to be considered. Therefore, there is every need to develop cheaper economic purification technologies. Let me also show you another important slide. If you look at the situation in 2000, we have 6 million people. Look at the relative sufficient area. 92% of the people have sufficient water. But look at 2025. We will have more than 8.5 billion people. The relative sufficiency is going to be reduced 60%. And look at the stress region. Stress people in 2000 only 5%. And 2025, see, it's going to be 31%. And if you look at the other region, where the scarcity, 3% is going to become 7%. Let me also quote my own country, India. India is going to be a highly water-stressed country in the coming years. Therefore, government of India is giving a lot of trust for water because India is the most populous country in the world now. Let me now talk about the global water crisis. Look at water is increasingly contaminated with so many pollutants. Oil, so Frank talked about oil today, nuclear waste, industrial waste, large number of pollutants are entering into water stream. Nanoplastics and microplastics are a very big issue now. Emerging pollutants. Mawa talked about emerging pollutants. You see, UV filters, gasoline additives, perfluorinated compounds, flame retardants, large number of emerging pollutants. Dear colleagues, if you look at the water purification technologies, we have chemical, biological, mechanical, traditional ways of water purification technologies. Today, I'm going to talk about how we can utilize cellulosic material, particularly nanocellulose, for water purification. Nanocellulose is quite important in terms of porosity. You can engineer the surface charge. Hydrophilicity, hydrophobicity could be controlled. If you look at the water purification technologies, you see, if you look at, there are a variety of processes. Microfiltration process can handle up to 10 nanometer to 1 micrometer size. Then ultrafiltration process can handle up to 10 nanometer size. Nanofiltration process and reverse osmosis can remove up to the But reverse osmosis, as you know, energy intensive process. You take away all the ions from the water. If you look at the membrane separation process, membranes have lots of advantages. High porosity, good mechanical strength, very good flexibility, wide range of pH stability, but lot of possibilities. You can see some of the pictures of membranes we have developed in my laboratory. If you look at the literature, the variety of polymeric membranes are available now. Polyvinyl fluoride, polysulfone, polyether sulfone, polyamides, polyacrylonitrile, cellulosic membranes, variety of membranes. Today, dear colleagues, I'm going to talk about nanocellulose membranes. Nanocellulose membranes are renewable. They are able to make it from waste materials, agricultural waste materials. And we can make nanocellulose or nanocrystals. You see, this is the low nanocellulose, maybe 2000, nanometer length, low nanocellulose. We can also make nanocrystals, short nanocrystals. And what we do, mainly in our laboratory, we do a steam explosion process, and we make nanocellulose and nanocrystals in our laboratory. Look at the nanocellulose we have synthesized. We have a company in the campus now making large-scale production of nanocellulose. First of all, I'm going to talk about how we can make use of how we can make use of this material to remove some of the dyes being utilized by the textile industry. So one of the dyes we focused is, crystal violet dye. And crystal violet dye, in order to remove crystal violet dye, what we have done is we made nanocellulose in our laboratory. We did a small chemical reaction on the surface of the nanocellulose. Very simple reaction, melted mass reaction. And we could introduce UO minus group on the surface of nanocellulose. You know why we have done this? If you do that, you can have electrostatic interaction between crystal violet and nanocellulose. Look at this. This electrostatic interaction. If you do that, you see you can separate out the dyes very effectively. This is the bottommost part is simply the PVDF type of membranes being used by the company for removing crystal violet. They're not very efficient. But if you coat with the nanocellulose on the surface of these commercial membrane, you see the red one is simple nanocellulose dispersion. We give a spray coating. And the top one is chemically modified nanocellulose with major masses. You see their suppression efficiency has gone up. And I've shown why, because of electrostatic interaction. You can see we could catch up most of the crystal violet. We will also, probably you all know that water is increasingly contaminated with suspended particles. Look at the membrane. What we have done is we looked at the commercial membrane, coated with the nanocellulose. And we made a model system in our laboratory. This is nothing but water with iron oxide particles. We filter through this membrane. You see all these iron oxide particles, range of 50 to 100 nanometer size, were stored on the top of the filter. Why? Because we made the whole size so small by coating the nanocellulose. And this is the bottom part of the filter, which is electrospheric. So, dear colleagues, we are able to, remove suspended particles. Probably you all know that water is increasingly contaminated oil. Professor Frank talked about the oil contamination. You can make use of nanocellulose aerogel. Look at nanocellulose aerogel. Very exciting work of Finland group. You make nanocellulose aerogel and you make the surface hydrophobic. Once you make the surface hydrophobic, all the oil particles should be absorbed by this nanocellulose. Water cannot enter because it is hydrophobic. And once the aerogel is swollen, dear colleagues, you squeeze out the oil or you burn the oil. See? Okay. So you can remove oil very well. The only thing is you have to do some sort of coating on the surface of nanocellulose. Titanium dioxide coating on the surface of the nanocellulose. You make it hydrophobic. Now let me show you another interesting thing. You can also make use of filter paper, removing oil from water. This is a normal filter paper. Look at this normal filter paper. This is hydrophilic. You know, filter paper is hydrophilic. But dear friends, if you go to the nanocellulose, look at the nanocellulose we have made from pulp. You make nanocellulose, you make it hydrophobic by a simple reaction. Octadecylamine, you react to octadecylamine, you can make the surface of nanocellulose highly hydrophobic. You coat the filter paper with modified nanocellulose, which is extremely hydrophobic, but it cannot penetrate, it becomes hydrophobic. And you see the experiment. This is the oil water mixer. You put that filter paper into it. The filter paper can take away all the oil. Why? You made the surface extremely hydrophobic by a simple treatment. And look at the water contact angle as a function of number of cycles. It's pretty stable, even after 9 cycles. So you can convert your filter paper extremely hydrophobic by simply coating with hydrophobic nanocellulose. Look at another interesting work my coworker did. We made hydrophobic. We made aerogel of nanocellulose. We went for a silylation reaction. And dear colleagues, we could remove most of the dyes, crystal violet dye from water by simple silylation reaction, hydrophobic interaction. So we could do a lot of chemistry on the surface of nanocellulose, and we are able to remove many of the pollutants. Look at the heavy metals. Dear friends, we can remove heavy metals. Look at the equilibrium absorption of chromium 6. You can achieve something like 92% chromium absorption using nanocellulose. Similarly, you can remove nickel, cadmium, lead. You see, there are 3 graphs here. The blue one is a rice straw, simple rice straw. Our great grandfathers usually use the rice straw or a wheat straw to separate heavy metals. You see, the efficiency is 50%. But dear colleagues, if you go to nanocellulose, the red one is nanocellulose, efficiency is more than 90%, 95%. We can also remove bacteria and viruses from water. So bacteria, they are quite bigger in size. You just simply give a coating to a commercial filter with nanocellulose is first. Now many companies, we coat their filter with nanocellulose because we make nanocellulose in the laboratory. But if you want to catch viruses are very tiny materials. So you have to do some chemistry. The best chemistry is you react to the polyvinylamine. When you react nanocellulose polyvinylamine, you introduce massive amine group on the surface of nanocellulose. And you all know that, viruses have a protein envelope which is negatively charged. So you can have electrostatic interaction. So you can remove bacteria and viruses. Look at the logarithmic, LRV, logarithmic reduction values. You see the viruses, it could be very close to, the value is very close to, sorry, let me go back. Sorry. Yes, if you look at the logarithmic reduction values of bacteria and viruses, it's a pretty high value. You see 6. Dear colleagues, you can also make many of the commercial electrospun membranes that are weak. I can show you a good example. Look at the PANS electrospun membrane. The strength is something like, okay, the strength is something like 3 megapascals. But if you coat with the nanocellulose, the strength would be increased to something like 4 megapascals. So many of the commercial electrospun membranes could be made stronger by nanocellulose. Same, they become more efficient because the whole size could be reduced. We can also make fiber structures. Look at nanocellulose and PVDF and nanochitin. We also work on PVDF nanochitin. You see, one of my colleagues in Europe, she was using PVDF type of membrane for removing indigo carmine dye from water. The efficiency was 22.3%. But if you combine PVDF and nanochitin, the efficiency becomes 80%. Now let me show you, we are also into biochar. We are able to make biochar from variety of agricultural ways. We go for a pyrolysis, controlled conditions. We are able to make biochar from different sources. And we are also able to do a lot of functionalization of the biochar, chemical modification, physical modification, so that we can engineer the surface quite effectively to catch many pollutants. So dye removal, pharmaceutical removal, pathogens, microplastics. And if you look at the surfaces of these, material, these biochar material, the surfaces could be engineered very beautifully. You can have electrostatic interaction, you can have pipe interaction, you have beautiful pores where you can have adsorption process, you have publication process. So a variety of chemistries could be done on the surface of biochar to remove pollutants. So you can see some of the biochars we have made in our laboratory. This is biochar. This is biochar chitosan material. This is biochar chitosan, modified with phthalate. And you can see, if you look at the variety of work has been done in different parts of the world, biochar has a lot of interest worldwide. And recently we made some interesting biochar. Maybe I'll show you. Look at the biochar we made from a plant waste at different temperature of pyrolysis. And this one, the biochar number 3, is the best one. You can see we could remove methylene blue by using biochar. So biochar is increasingly quite interesting material for water purification. So we are doing a lot of work in this area. Finally, let me conclude. Nanocellulose is a very interesting material for water purification. You can do the required paint on the surface. You can remove dyes. You can remove bacterial viruses. You can remove heavy metals. You can remove oil. A variety of pollutants could be removed from water by using nanocellulose. It's extremely renewable. And we are also working in the field of biochar. And we are able to manipulate the surface of biochar, and you can put the right chemistry on the surface of biochar to remove a variety of pollutants. And many, many thanks for your patient hearing. Thanks a lot. Dear colleagues, I also wanted to show you, I'm the editor of Nanostructures and Nano Objects. So if you work on nano, please submit your article. And one more point is, we also have a conference coming up. We also have a conference coming up in India. Sorry, I think this is not on the slide. Thank you. Thank you.
Thank you, Sabu, for this interesting presentation. Are there any questions?
Thank you for the interesting presentation. Thank you very much. We would like to ask about the range of pH admissible for the stability of the cellulose membrane. Thank you.
It's got a wide range of pH tolerance. That's the beauty of nanocellulose. Wide range of pH tolerance it can work. Yeah. Yes. That's the beauty of this material. Wide range of pH tolerance level. Yes.
As before, the previous cellulose membranes were very sensitive. I think it's value.
Pardon?
The previous cellulose membranes were very sensitive to pH value.
Whatever experiments we have done here, the pH was very close to 7. Yes, but we also did some acidic pH values. It was also quite efficient. So we are able to work on a range of pH values. Yes.
Thank you very much.
Thank you.
Are there any further questions? If not, I would like to thank you.
Thank you.